Hi everyone, this is a lesson number 10 on statistical methods in high-energy physics. The last two videos were about the maximum likelihood method and how to estimate uncertainties of the maximum likelihood estimators. There were so many things to tell you that I kept back from you a very important information. There's an easy way how to identify a particle physicist. When you hear someone talk about statistics, and every other word she or he says is fit, then that person is probably a particle physicist. With this word, particle physicists don't want to say that someone is in a good condition or that something is just the right size. They use the term fit instead of more conventional model parameter estimation. So when you hear someone saying, "I fitted data with the Gaussian," you should realize that that person is a particle physicist and that he or she just estimated parameters of their Gaussian model with the use of some data. You will hear the word fit many times in this video. Let's have a look at a couple of special use cases of the maximum likelihood method. The first one shows how extraordinarily simple it is to combine measurements with this fantastic method. Imagine you want to determine how much spare money people have in a certain country. Your available data could be, for example, number of luxury watches sold and the amount of lager beer people drink. Each of them probes different aspects of the liquidity, let's call it theta, but both of them are sensitive to it. Let's denote our data about the luxury watches as x vector and the data about the lager beer consumption as y vector. They are of course distributed according to different probability density functions, and let's denote them as f of x vector theta and g of y vector with parameter theta. Provided that the two measurements are independent, the joint probability density function is just a product of the two functions. F joint of x vector, y vector with parameter theta equals to f of x vector with parameter theta times g of y vector with parameter theta. Therefore, the overall log likelihood function is a sum of the two log likelihood functions. Log of L of theta equals to log of f joint of x vector obs y vector obs with parameter theta, and that equals to log of f of x vector obs with parameter theta plus log of g of y vector obs with parameter theta. Obviously, the precision of the theta measurement is higher when the two independent sets of data are combined. A very typical use case in particle physics is a combination of data from different decay modes of a particle. For example, the Higgs boson discovery was based on a combination of data from several decay modes, and the most important two were the decays of Higgs to 2 photons and Higgs to 2 Z bosons, which then in turn decayed into 4 leptons. The latter case was itself a combination of data from several decay modes of the 2 Z bosons, ZZ going to 4 electrons, ZZ going to 4 muons, and ZZ going to 2 electrons and 2 muons. Another very common example of a combination in particle physics is the usage of control regions. An analysis defines a so-called signal region, which is a region of data space in which most signal data events are expected to appear. Unfortunately, some events originating from other processes, the so-called background, are also present in the signal region. A model describing the background is typically very complicated, and it contains unknown parameters. The signal region, ideally containing very little background events, doesn't have enough statistical power to determine that background parameters values with a sufficient precision. Therefore, people introduce control regions that are insensitive to signal but are sensitive to background processes. A joint likelihood containing data from both the signal and the control regions determines the background-related parameters much better. Let's switch topics and talk about another situation that is extremely common and therefore important in particle physics. When working with the Monte Carlo simulated data, you have to work with weighted events. One reason is that we usually weight the simulated events so that the sum of weights corresponds to the expected number of events observed in real data sample with a given integrated luminosity. If we use multiple Monte Carlo samples to describe processes with different cross-sections, then this weight will differ from sample to sample, and we will end up with a mixture of different weights in our full Monte Carlo dataset. Another reason to weight Monte Carlo events is to cure imperfection of our simulation of detector response. Since the simulation is not perfect, our analysis selection criteria might have different impact on the Monte Carlo simulated data than on the real data. To remedy this, people measure correction factors and apply them as weights on Monte Carlo events. These weights usually depend on the kinematics of the event, and therefore each event is assigned a different weight. Another common reason are NLO, shortcut for next to leading order, Monte Carlo generators. Unfortunately, these wonderful tools come up with weighted events too. Let me say openly that it is very difficult to work with weighted data in a rigorous way. We will not try to do it in this video at all. We will rather look at some shortcuts that people use when they face this complicated problem. Let's take some data x vector and let's assume each event xi has a weight wi. For simplicity, let's assume that each event is drawn from the same probability density function f of xi with parameter theta. A natural extension of the joint probability density function is a product of the probability density functions f of xi theta, where each term is raised to the power of wi. F joint of x vector with parameter theta equals to product for I going from 1 to n of f of xi with parameter theta to the power of wi. Of course, this function needs a different normalization that takes the weights into account, but let's not struggle with it at the moment. Anyway, the meaning of the modification is probably clear to you. Effectively, each event is represented wi times in the joint probability density function. Also, one could view it on the log likelihood function that becomes a weighted sum of the log likelihood functions corresponding to the individual events. Log L of theta equals to sum for I going from 1 to n of w sub I times log of f of xi obs with parameter theta. It is interesting and quite important to realize what happens if the probability density function for the events xi is Gaussian. The joint probability density function for the set of weighted events is then f joint of x vector with parameters mu and sigma equals to product for I going from 1 to n of 1 over square root of 2 pi sigma squared over wi times exponential of xi minus mu squared over 2 sigma squared over wi. Effectively, each term in the product is again a Gaussian function with sigma prime squared equal to sigma squared over wi. Then the maximum likelihood estimator of the mean value is a weighted average. Mu hat equals to sum for I going from 1 to n of wi times xi over sum of weights wk. This is a very intuitive result. Also, no surprise that the expectation value of this estimator is equal to the true value of the parameter mu. The variance of this estimator is in some sense very intuitive as well. Variance of mu hat equals to variance of 1 over sum of wk times sum of wi times xi. Now remember the properties of variance. 1 over sum of wk is just a constant, so we can take it out of the variance, but it will be raised to the power of 2. So we get 1 over sum of wk all squared times variance of sum of wi times xi. We can continue. wi's are again constant, so we can take them out. So we get 1 over sum of wk squared times sum of wi squared times variance of xi. Now remember that we consider each variable xi sampled from a Gaussian raised to the power of wi. We have written the variance of such a probability density function just moments ago. It's equal to sigma squared over wi. So we can continue our calculation. The expression equals to 1 over sum of wk all squared times sum of wi squared times sigma squared over wi. And this equals to sigma squared over sum of wi. Recall that for unweighted events, the variance is sigma squared over n. With the weights, when each event effectively contributes wi times, the number of events is replaced by the sum of the weights. This should immediately raise a red flag. There is something wrong with this estimate. By increasing the event weights, we can make the variance arbitrarily small while still using exactly the same number of original events. The point is that the events are actually not drawn from the probability density function raised to the power of wi. They are drawn from the original probability density function, and the weight is assigned to them afterwards. So if we have a set of 101 events, 100 of them with a weight of 1, and one event with a weight of 1 million, then the weighted average is pretty much equal to the value of the event with the large weight, and we can safely ignore the other 100 events. Effectively, we have estimated the mean mu hat by using just one event drawn from the original probability density function. So the variance of this estimate should equal to the variance of the original probability density function. This is not what we got before. To remedy this, we compute the variance with the use of the original probability density function, without raising them to the power of wi. Using our previous example with the Gaussian probability distribution function, we get the following result. The beginning of the calculation is exactly the same as before, only this time the variance of each xi will just be sigma squared. So we get the expression equals to 1 over sum of wk squared times sum of wi squared sigma squared, and this equals sigma squared over sum of wk all squared over sum of wi squared. The number in the denominator is called effective number of events. This expression is definitely worth remembering, so let's write it down again. N effective equals to sum of weights wi all squared over sum of weights wj squared. One can clearly see that this formula is asymptotically well behaved. If all the events have the same weight, it is equal just to the number of events n. N effective equals to n squared times w squared over n times w squared, and that equals to n. On the other hand, if we have one event with significantly larger weight than all the other weights, the effective number of events becomes 1, because we can neglect all the other weights in the sum. Let's remark that the previous definition of the means estimate variance, the one using the sum of weights instead of the effective number of events, has also its use cases. We would use it if we wanted to use a Monte Carlo sample to study prospects of future experiments, or when estimating the amount of luminosity needed for a good measurement. It tells us what the precision of our mean estimate would be if we had the amount of unweighted data corresponding to the sum of weights. We have just demonstrated how to correctly estimate uncertainty of the estimate of the normal distribution mean for weighted data. But what about other parameters? And what if we do not use the normal distribution? One can be tempted to use the weighted log likelihood function and then continue with the method of maximum likelihood exactly as before. You should know that this approach will give you the correct estimate of the parameters, but you will not get the correct uncertainties if using either the graphical method or the method based on the Fisher information matrix. In other words, when using the two most common methods. Concretely, you will get uncertainties that behave similarly to the first estimate of the weighted means variance and will scale with the sum of weights rather than with the effective number of events. There are several ways of how to deal with this problem, but going through them is beyond the scope of this lecture. We will just note that RuFit library in a root framework offers two correction methods for the estimated covariance matrix, which can be switched on by adding a SUMW2 error or asymptotic error command arguments when calling the RuFit's fit2 method. Finally, let's discuss a very important connection to a situation that is a bit different but of an ultimate practical importance. When working with Monte Carlo and histograms, one always needs to estimate an uncertainty in a histogram bin due to the limited statistics of the Monte Carlo sample. The bin content is estimated with the sum of event weights. B hat equals to sum for I going from 1 to n of wi. This time, we use n as the number of events that fall into our histogram bin. To study properties of this estimator, let's split our events into categories according to the weight they receive. All events within a category receive the same weight. Let's assume there are w such weights. Therefore, we can calculate the bin content as a weighted sum over the categories. B hat equals to sum for I going from 1 to w of wi and I. The numbers ni stand for the numbers of events in the individual categories. A good approximation is to treat all the numbers ni as distributed according to the Poisson distribution. Then the obvious question is, what is the variance of the bin content? Again, we use the properties of the variance. Variance of B hat equals to variance of sum for I going from 1 to w of wi and I, and this equals to sum of I going from 1 to w of wi squared times variance of ni. Remember that the variance of the Poisson distribution just equals to nu I, so we get sum for I going from 1 to w of wi squared nu I. As an estimator of the variance, we can replace the mean values by the observed numbers of events n I. We get estimator of variance of b hat equals to sum for I going from 1 to w of wi squared times ni. As a final step, we can write the estimator with the use of the individual events. Estimator of variance of b hat equals to sum for I going from 1 to n of wi squared. A simple estimator of the standard deviation is, certainly, square root of the variance. More often, we are interested in so-called relative uncertainty, which is the standard deviation divided by the bin content. Sigma hat relative equals to square root of sum of wi squared over sum of wi. The last formula can be rewritten with the use of the effective number of entries. Sigma hat relative equals to 1 over square root of n effective. Again, the effective number of events lives up to its name. If all event weights were equal, then the effective number of events would be equal to the number of events, and we would get the notoriously known formula for the estimate of the relative uncertainty of a Poisson distribution. The data analysis framework root offers the possibility to estimate the histogram bin content uncertainty with the use of the effective number of events. Just call the method th1 sumw2 before filling the histogram. Never forget to call this because it is a very suitable uncertainty estimate in most situations. We've just touched the topic of histograms, and let's expand on it now. People often aggregate data consisting of individual events into histograms. The wonderful thing is that we don't need to modify the maximum likelihood method in any way if we decide to work with histograms rather than with the sets of individual events. To explain this, let's clarify what the word event can stand for. In one of our previous videos, we asked Cristiano Ronaldo to shoot a ball at its maximum speed many times. Our aim was to determine an average speed of his full force kicks. From the statistical point of view, each shot is a process of drawing one number from a probability density function. Let's denote the probability density function as f of x with parameter theta. We called the shots events, and we wrote a joint probability density function for the set of events as a product of probability density functions for individual shots. In pretty much the same spirit, we can create a histogram of the shot speed and consider each bin as one category or event. The overall probability density function is then a product of probability density functions describing our events, one probability density function for each bin. These per bin probability density functions are different from each other, but it doesn't matter. The thing that matters is that we are able to construct the probability density function corresponding to our event. An extreme case of such approach is so-called cut-and-count experiment, in which people just count an occurrence of certain effects. For example, you run the LHC accelerator a couple of years, you collide quadrillion protons, and you count collisions passing some selection criteria. Effectively, you drew one number from some probability density function that is typically a Poisson distribution. With this number at hand, you can estimate some model parameters that interest you. Coming back to histograms now. Let's assume Cristiano promised to kick n shots and he kicked exactly n times indeed. Our measurement can definitely be described by a vector x in an n-dimensional space. Each component is the speed of some specific shot. This would be the most detailed description. However, we can do a shortcut and use a much shorter vector n that stands for a histogram. Each component is the number of shots in a specific bin. Given that the number of shots is fixed, the probability density function for our histogram n is a multinomial distribution. F of n vector with parameter theta equals to n factorial times product for I going from 1 to n bins of fraction of nu I with parameter theta over n, this whole to the power of ni over ni factorial. Here, nu I with parameter theta is the expected number of shots in the bin I. Clearly depends on the model parameter theta. Actually, it is given by an integral of the probability density function for the speed of one shot, f of x with parameter theta, over the bin range. Nu I of theta over n equals to integral between xi min to xi max of f of x with parameter theta by dx. And that's it. We can insert the observed histogram n vector obs to get the likelihood function. After that, we can minimize the negative log likelihood function to find an estimate of our model parameter. Of course, we also need to estimate the variance of our estimate, but we have already covered that in the previous videos. When we have it, we wrap our study, call Cristiano the results, and go home. Most probably you realize that the previous example was a little bit artificial because of the agreement with Cristiano to kick exactly n times. Most likely, we would let him to shoot, let's say for 2 hours, and then the number of shots wouldn't be a pre-agreed fixed number, but it would be a random variable. Then the probability density function would be a product of a Poisson distribution to account for the number of shots, and a joint probability density function for the shot speed. F of n and x vector with parameter theta equals to nu to the power of n over n factorial times e to the power of minus nu times product for I going from 1 to n of f of xi with parameter theta. The expected number of shots, nu, might and might not be a function of theta. If it is a function of theta, then the number of shots itself is a measurement sensitive to theta. Therefore, we expect our estimator of theta to have a lower variance than if it didn't consider the number of shots in our model. In the present case, it will probably be a function of theta because there should be a relation between the number of kicks one can deliver and their speed. People aren't robots. When this probability density function is used in the maximum likelihood method, then we refer to it as the extended maximum likelihood fit. The probability density function for the histogram can be extended in exactly the same way to account for the randomness of the number of shots. We just multiply it with the Poisson distribution. The result is quite remarkable. Let's write it down. F of n vector theta equals to nu with parameter theta to the power of n over n factorial times e to the power of minus nu with parameter theta times n factorial times product for I going from 1 to n bins of nu I with parameter theta over nu with parameter theta to the power of ni over ni factorial. Note that we express the probability for an event to fall into the bin I as nu I over nu. Still, the formula doesn't look too attractive yet, but we can shape it to much nicer form. Just realize that sum of nu I equals to nu and sum of ni equals to n. Then we get f of n vector theta equals to product for I going from 1 to n bins of nu I with parameter theta to the power of ni over ni factorial times exponential of minus nu I with parameter theta. Here we go. The probability density function is a product of independent Poisson distributions. Each Poisson term stands for the content of one bin. This result is of a huge practical importance in particle physics, where histograms are extremely common. Moreover, the number of events is almost always a random variable in particle physics. There, an experiment is not defined by a fixed number of occurrences of something, but rather by an integrated luminosity at colliders, nearby nuclear power plant output, in neutrino physics, and so on. The data analysis framework route offers a very comfortable interface for fitting of histograms. You just prepare your model as a TF1 object and call the histogram method fit with certain options. If you use h fit model, quotation mark WLI quotation mark, then you are fitting your function model to the histogram h with the use of the extended bin log likelihood method. The option L specifies this method. With the option W, the histogram is treated as weighted. In this case, the method th1 sum w2 must have been called beforehand. The option I determines how the Poisson expectation values are calculated from the fit function. With the option I, the function is integrated over the bin range as described a short while ago. Without it, the expectation value is estimated with the use of the function value at the bin center. This is much faster and usually sufficient approximation. Let's open the last topic of this video. Up to now, we treated all model parameters as completely unknown, unconstrained, untouched. They just appeared in our model and that was it. However, it is very common that we have some knowledge about some of the parameters before doing our measurement. Very typically, there are previous measurements of the sum of the parameters. Ideally, we would combine the measurements in the same way as outlined before, by including the corresponding probability density functions to our model, building the overall likelihood function and fitting its maximum. In practice, this is very rarely done, because such a complete information is almost never published. A published result is most often in the form of the parameter estimate together with a confidence interval or just a standard deviation. The necessary information is not even available if the previous or supporting measurement comes from the same experimental collaboration, not to mention if it comes from some old and long-forgotten experiment. However, there is a very elegant workaround for incorporating the previous measurements into our fit model. This workaround is actually a Bayesian element in the frequencies framework that we've been building up to now. In the Bayesian framework, it is possible and very common to have probability distributions for the model parameters. Recall that this is contrary to the frequentist approach where model parameters are not random. However, if we leave the realm of strict frequentist statistics, we can profit very much from the flexibility offered by the Bayesian framework. Based on the result of the previous or supporting measurements of some parameter of our model, we build a probability density function for this parameter. Most commonly, we assume that this probability density function is Gaussian, with the mean value equal to the previous measurement estimate and sigma equal to its uncertainty. Namely, theta is distributed according to g of theta, which equals to the normal distribution of theta with parameter mean, theta hat, and sigma hat of theta hat. In the particle physics jargon, the function g of theta is typically called a constraint term. There are several types of commonly used functions for the constraint term, but Gaussian is often the first pick. Then we just multiply our model with the constraint term to get, for example, likelihood of θ1 and θ2 equals the product for I going from 1 to n of f of xi obs with parameter θ1 and θ2 times g of θ1. Note the role of the constraint term in the overall likelihood function. This favors values of the parameter that are far from the estimate made by the previous measurement. And this favors them by decreasing the likelihood value whenever the parameter value deviates from the estimate. However, the maximum of the likelihood function isn't located at the maximum of the constraint term, because there is the experimental data xi obs that, by themselves, can favor a different value of θ1. The result is a sort of compromise between the constraint term and the unconstrained model f of xi obs θ1, θ2.